We have angled the sensors as in previous experiments to provide peripheral perception. However, this time we have mounted them at the rear of the robot, in line with the rear axle, to provide a much tighter control feedback. This enables the robot to maneuver in very close proximity to obstacles. Many wheelchair users, according to research, have some difficulties in passing through a doorway or a narrow gap between obstacles. Potential assistance offered to the users from an automated system can be seen as the robot aligns itself to the doorway. When the door is closed, the robot stops and waits. When the gap is sufficient to pass through, the robot proceeds. No logic or heuristics are employed. We can also clearly see that the robot velocity is also proportionally reduced to zero as the gap minimizes. Repeatability is important in research, and we demonstrate the robot performance as it approaches and leaves the same obstacle set up several times. Sensor perception essentially allows any trajectory to be manipulated to take into account dynamic and static objects. We can see the slight variation in path each repetition. By opting for a more localized, repulsive field, the flat area between obstacles allows the robot to take a more natural path, rather than a rigid mechanical one, like line following, for example, which is effectively like travelling on rails. This natural behaviour is more suited to a real-time application for mobile assistive devices, particularly when the need for user empowerment is part of the patient care and rehabilitation. This experiment confirms that localized potential algorithms allow for tight maneuverings either when employed rotationally only or simultaneous rotation and translation with a smooth transference between the two. As in the previous experiments, dynamic interruption either causes the robot to deviate when in close proximity or stop when the available free space is less than that required to safely pass through.